Okay, just a few little bits of housekeeping before we get going. People are asking me questions and all this information is out there. You need to look yourself. If you do go to the Moodle site, you want to know a bit more about how the bridge is being tested, there's a video here. I can't get it to work, but there's an MPG video. Go in, have a look, watch it, and you'll see what a test looks like. Unless I can get this, I don't know why this isn't doing anything. Okay, with respect to the bridge project again, what I want to make clear is I really want you to build the lightest possible bridge. You will not lose marks if you've built a bridge so light and it fails under testing. Okay, the aim is to build the lightest possible bridge. No marks will be lost if your bridge fails. The only time you will lose mark is if your bridge is too heavy, if you didn't actually measure it and it doesn't fit the rig, so it can't be tested, and you didn't fill in the A4 sheet. So the only thing you're handing in is an A4 sheet that has your names on it, that we actually write the weight of the bridge on, and that you write a couple of sentences and or draw a picture saying what your bridge is, whether it's a truss, an arch, a beam, a combination, and the structural form, the structural actions. So you do all of that, you will automatically get 5%. But I don't want to see lots of boring, heavy bridges because I'm going to get bored. And I want you to make it interesting. Like I try so hard to make it interesting for you. Whether I achieve that or not is a different matter. So that was what I wanted to say about Project 2. And I will email everyone because half of you are not here. Where are you? Not you guys here, the people that aren't here. Shame on you. Turn up to something for once in a while. Okay, with respect to Project 3, one thing I didn't mention is the loading. So this project is continuing from Project 1, so you don't have to go out to site and measure it again. You use the same measurements from Project 1. You use the same loading for the concrete slab, for the live load, pedestrian live load, for the roof live load, for the weight of the roof, for the weight of the handrail. So the only loading you will change is what you allowed for the self-weight of the truss. And when you did your Project 1 trusses, you assumed your truss members weighed somewhere between 10 and 20. For this part of the project, for your main beams, you're going to assume they weigh 70 kilograms per metre as a starting point. And as I said, you are then going to work out how big the beam has to be, then go back and redo the calculation with that actual weight in there. Now there is a 20 kilograms written here because you also have to design what I call the secondary beams as well. Now when you previously did your truss, oh, and I don't have a picture here, let me get a blank screen somewhere with a bit of room. Nowhere. Hang on. In this truss here, you of course had, this was a different structure which is why it looks so tall and thin. Your truss footbridge looked like so. Now you didn't design them, but hopefully you can all appreciate there were members running under the concrete slab between the two trusses holding them together. And we refer to these as our secondary beams because they are secondary to the structure. The way this thing would be built is you would put the trusses up, you would put the members in between in there, and you would put the concrete slab on top. And that gives you an indication of the load path. The weight of a pedestrian would go from the concrete slab into these secondary beams, and then the secondary beams effectively span between the two trusses. So you are going to design these beams here as simply supported beams, however wide your trusses were. I think most of them were between 2 and 2.5 metres wide. And the load on these beams will be the load from the weight of the concrete and the people on them, so a uniformly distributed load. So you have to design them as well, and the starting point weight for those would be assumed to be 20 kilograms per metre. However, when you come and design these beams, your starting point would be 70 kilograms per metre. There's also one other difference, that relates to that extra steel work. In the truss, you allowed for an extra 20%. In this instance, your extra steel work, you will, I think in the brief, it says to allow for an extra 20 kilograms per metre. And that's to allow for the roof steelwork, okay, because there's more steelwork involved now, because you've got your main beams and then steelwork up from that. So you don't get your knickers in a knot about how much does all this roof steelwork weigh. Assume it weighs 20 kilograms per metre. Once you actually design your secondary beams, you will put their weight in as part of the weight on your main beam. Okay, that's enough, I think. So I would get going on my loading now. You as yet can't do your serviceability limit design of your bridges, but you can do your ultimate limit state design for task 1 and 2, half of 2. So I would get going. Now, there are certain tricks in there, not tricks, certain surprising things that happen. If you leave this to the night before and you come across these things, you're going to panic and go, oh my God, I don't know what to do. So I do strongly suggest you get the groundwork done now, so when you hit those problems, you can come up to me before the lecture, go up to your demonstrator, go to the help desk and say, oh, this is happening. Not quite sure how to deal with it. Okay? So there are various hurdles in there. So be aware, don't panic, they've been put in there on purpose, so to speak. Okay, they are the two bridge. So they're all I want to say about the projects. And now we are continuing, not with something really interesting yet, but we're doing something pretty interesting. That something being deflections. So you gave me 2 minutes, was it, at the end of the last lecture? So I will just go over all of that again. Hang on, this is in lecture mode. I don't like that because there's all these lights on me. Room settings. That's better. Not in the spotlight now. Okay, very, very importantly, in terms of design, just as much emphasis is put on deflection checks, serviceability limit state design, as is put on ultimate limit state design. But Lizzie, it's not as important. You have smaller load factors, I suppose, to allow for that. When you actually do your formal design, just as important. Things are not allowed to deflect too much. So, as I said, the main serviceability requirement is deflection. Other serviceability requirements would be vibration if you were dealing with a sports hall, or if you were looking at the fire rating of a building, ensuring that they were designed to ensure that this building would stand for a certain amount of time. There's a certain requirement, time limit, so people can exit the building without it falling down on them. These deflection limits are important for a number of reasons. 3 of them are: 1, so people on the building don't panic because they can feel the building moving under them, so to minimise the perception of excessive movements by the occupants. To limit just the unsightly appearance of sagging. No one likes saggy baggy stuff. And just to ensure any attached connected surfaces or machinery or cladding, ceilings and walls can perform, particularly with machinery. Certain machinery have to be sit horizontal, and if your floor underneath starts moving too much, that could cause problems. It talks here to prevent unintended load paths. An example of that is if you have a just check I'm on pen mode. If you have a floor that carries a high load and it sags, and under the floor you have a wall underneath, but that wall isn't meant to be a load-bearing wall. Have you heard of the expression load-bearing walls and non-load-bearing walls? If that wall was not designed as a load-bearing wall, but the floor above it starts sagging too much, it will start applying load to that wall, and then that wall would typically crack. Okay? So we don't want load paths to change. And then if that does then shed load into the wall, that wall possibly will carry some of that, but then may shed it down to a bit of floor that was not designed to carry that extra load. So that then may in turn cause something else to fail. As I said, there are different deflection limits depending on what you are actually designing. So when it comes to a floor, it's very important that the live load deflection isn't too great. When it comes to roof rafters, it's more important because there isn't a lot of live load up there. When you are walking on the roof, okay, it moves a bit. You expect it to move a bit because it's just you're up there for maintenance. But under the dead load, you don't want any permanent deflections in there, particularly if it's a flat roof. And then you would get cases of water collecting, water ponding on there and causing further deterioration. So we're, as I said, only going to consider one, and that's a combination of dead and live. Now, when we dealt with serviceability, ultimate limit state design, we increased our dead and live load. Okay? And that increase meant our failure was minimised. The chance of failure was minimised. If you see here, we're actually reducing our live load. And that's because the live load we're starting off with is actually quite high. So I said for this space out here, this space would be designed typically for 3 kPa. 3 kPa is the equivalent of 3 100 kilo people every square metre. Now, that will probably never ever happen. Okay? And because it will never ever happen, we still have to design for it when it comes to strength. We get that 3 kPa, we multiply it by 1.5. But in terms of deflection, that's actually quite a high load. So we actually reduce the deflection. We're reducing it down to 2.1. You'd probably still never ever get 2 100 kilo people per square metre up here. If you do get those 2 people up here, you may get a little bit of cracking. If we were on a first floor, it may start deflecting a little bit, but I would be more concerned about the 100 kilo person squashed up against me more than the fact I probably wouldn't notice the floor is deflecting too much. So in terms of perception, that probably isn't as much of an issue. So yes, when we look at serviceability, our factors, load factors are different. And what you have to be clear about is people see these 2 loads and go, well, of course, ultimate's always going to be critical. Lizzie, look at the loads. They're so much higher. You have to be aware you are checking completely different things. When you look at serviceability, we are calculating a deflection and making sure it's not too big. When we do a strength check, you all know now, we calculate forces and stresses, and we make sure the material doesn't fail. So we do completely independent checks. So that's when you're doing your projects, the best thing is to design a member for strength, do an ultimate limit state check, come up with the member required, do the same thing for deflection, come up with a member required, and then say, I need to choose the bigger of the 2. Okay? So the maximum limits, we know the maximum stresses typically are the yield stress. When it comes to deflection, maximum deflections for a simply supported beam, which is what you have in your project, would be span on 250. So whatever your span, the distance between your supports is, if it's 10 metres, working in millimetres, that would give you an allowable deflection of 40 millimetres. Okay? Okay, so how do we calculate these deflections? This is what we need to know how to do. And today is really, really interesting because finally you have a practical reason for learning how to integrate. So this is one of the reasons you learnt how to integrate, to calculate deflections. Okay, So deflection we define as being y, and so we want to know what the maximum deflection is. Now, in saying we define it as being y, please do not confuse it with this y. So this y, in our stress formula, which is the distance from the neutral axis, is a different y. Okay? So we're a bit lazy and we use y to represent two things. Don't get the two muddled up. Now, a couple of lectures back, I actually derived this formula here, which is the formula linking moment to curvature. I said numerous times when something curves, if it's curving, you know there is a bending moment in it. If it's stretching, you know there's a tensile axial force in it. If it's in compression, you know there's a compressive axial force in it. If it's bending, if it's curving, there's a bending moment in it. And those two variables, moment and curvature, are linked by Young's modulus and the moment of inertia. So we know what moment is, we can derive that, we know what E is, we know what I is, what the hell is curvature? We want to know Y. How do we get from K to Y? So we have to look now what is curvature. It's the rate of change of the beam slope. So the rate of change of slope. So in saying that, slope is dy dx. dy dx. Now some of you again may be looking at this and saying, hang on a minute, dy dx is not equal to theta, it's equal to tan theta. Now, I've said previously that we are assuming small deflection theory here. That means our beams are not deflecting a lot. So these angles we're dealing with are very small. So they're very small angles. And when you do get a very small angle, something of the order of 0.5 degrees, and you convert it into radians and you take the tan of it, when deflections are small, in effect tan theta is equal to theta. So try it on your calculators at home, but not in degrees, in radians. So because of this small deflection theory we're assuming it because it is accurate enough to assume it. It is true, the case. Okay? Our dy dx is equal to theta, so is equal to our slope. Okay, so now we have a deflection y. And note, when you calculate deflections, normally they will be negative because we are using up as being positive. So in these formulas we're generating, y will typically work out to be a negative value. So we have a value for y. We know a slope is dy dx. How do we get to curvature? We can express curvature as a function of dy dx by actually going back and looking at a beam curving. So this blue line here represents a beam curving. And one of the other assumptions of small beam theory is that we apply a pure moment, so the curvature at a point is actually a circle. So we assume the curvature at a point to be a circle. So if we want to know what the curvature is, what the change in slope is, at point P we draw a tangent, and that tangent lies at an angle theta. At point Q we draw a tangent shown in green here, and that angle lies at theta plus d theta, or delta theta. And the change in slope is actually the change between those two, divided by the distance between them, ds, or delta s. And thus, we now can link curvature to, well, d theta ds. So for a sector of a circle, shown here in pale yellow, if r is the radius of my circle, if my angle in here is d theta, therefore we know for a circle that r d theta is equal to ds. Hopefully this is just bringing back memories of maths. And thus, my curvature, in saying it's d theta ds, I can relate it to the inverse of the radius. And this is a bit of a step here. With a little bit of mathematical manipulation, d theta ds is equal to d2 theta dx, d2 y dx squared. Now, you're all sitting there going, care factor is 0, but some of you are sitting there going, I wonder how she got that. So to save you wondering, I have scanned in my favourite maths textbook, And the proof of how you get from d theta ds to d2y dx squared is in there. So have a read through this wonderful proof to put you to sleep tonight. I shouldn't say that because I think this is really interesting stuff actually, and hopefully you do too. So anyway, we now know that curvature can be written as d2y dx squared. So we now have a relationship where our moment can be expressed in terms of y. Well, d2y dx squared. How do we get from d2y dx squared back to y? Well, you integrate twice, don't you? So y is equal to the integration of curvature. Curvature is equal to m on EI. So what we need to do is we are going to come up with a general expression for our moment, and then we integrate that, and lo and behold, that will get us to our deflection. So just going back here now. So this formula here we call the Euler-Bernoulli equation, named after the two people, Euler and Bernoulli, who came up with it. Bit of a partnership project there. And it's a very important equation, and you'll see it a number of times, and it's one to remember. So now, just looking at all our forces and our deflections, we now have a way to actually link our load to our deflection. Now, I've said it so many times, the relationship between shear and moment. Shear is equal to dm dx. And I also showed you a number of times that W is equal to dV dx. That gets us to moment. We now have this wonderful equation that links moment to curvature. You integrate your curvature expression once, you get slope. You integrate it a second time, you get deflection. So in theory, you can get an equation for your deflection, differentiate it twice, stick an EI out the front of it, differentiate it another 2 times, and that will actually get you back to the load. So these 1, 2, 3, 4, 5, 6 variables are linked mathematically by being one integral apart everywhere. Now, in saying you can do that mathematically, I don't ever really want you to do it mathematically to get from load to curvature. We do have to do the maths now. There's no way to get to deflection other through curvature. Okay? But just for you to be aware that the maths in here is beautiful. It's very, very nice. You've got to appreciate it. Okay, so how do we get deflection? We do a double integral on our moment on EI equation. So we need to know what the moment is. Now, we know the moment in the beam is not continuous, and that's why a couple of weeks ago, before I showed you the graphical method, I actually said we need to come up with equations for our moment, general equations for our moment in terms of x. And we needed to do that because we need that now. So you've effectively seen it before, so me talking about it again now, hopefully you won't be sitting there confused at all. A bit of revision now. Okay, how do we calculate this moment in terms of x? You've all had a week off, you've all forgotten. What do? We cut the beam, a general distance x. We draw, very importantly, a free body diagram. How do you draw a free body diagram? You draw a closed loop boundary around the area, around the structure you want. Then you redraw that structure with all the known reaction forces and all the known acting forces and the unknowns where you've actually cut through the beam. And you know we can cope with 3 unknowns because we have 3 equations of equilibrium to solve for those 3 unknowns. But what we want now is to come up with a mathematical expression for our moment. So here we have the case of a uniformly distributed load, W, on a beam of length L. So we can work out our reactions very simply because of symmetry. We cut the beam, a distance x. We're trying to come up with a general expression for our moment. And where do we take moments? We always take moments at the cut because that's the easiest place to take moments. Taking moments at the cut, we have m, which is our unknown moment. Then we have our reaction here times the distance from the cut, x metres. Our uniformly distributed load here now, referring just to our free body diagram. The total load down here is Wx, not WL. That was the whole shape, the whole structure. We're looking just at the free body diagram. That equivalent load we position in the middle of the beam, so a distance x on 2. So you can see here your Wx times x on 2, and now we have an expression for our moment. And now instead of moment, we can say, okay, well, as well as equal to moment, that is also equal to EI d2y dx squared. So now we just integrate. Isn't that nice, mathematically speaking? Look, you've done lots of maths and you're here in engineering, so nod your heads because you should be able to appreciate this nice maths. Okay, so here's our expression for our moment. So instead of moment now, well, I'm now going to express it as d2y dx squared. And I know you can all do integration, so I don't have to focus on that. So we integrate it once. So our x term becomes an x squared term, our x squared term becomes an x cubed term. And very importantly, you have to plus your constant of integration, plus C1. Now, what is that telling us? That is giving us the slope. So, if I wanted to know the slope at the support here, dy dx, once I know the value of C1, I would then say here, when x is equal to 0, dy dx is equal to, and I would put values in and calculate it what it's equal to. So wherever you want to know the value of the slope, you would put that value of x in. Okay, slope's not so exciting. We integrate it a second time and we get deflection. So x squared becomes x cubed becomes x to the power of 4. And we then have our second constant of integration. So it's not that simple yet. We have two unknowns we have to solve for. But those two unknowns can very simply be solved for. Okay? And we use known boundary conditions. So they're known. So solve for the constants of integration using boundary conditions. And they're known values of the deflection or slope on the beam. And you always have at least two known values. What are those known values? At the supports, when you have a simply supported beam, this is not rocket science. People go, I don't know what my boundary conditions are. Simply supported beam, there is no movement at the supports. So in this case here, when x is 0, y is 0, when x is L, y is 0. Sometimes you guys read too much into things. You want to make things more complicated than they really are. Very simply, two boundary conditions, we can solve for our two constants of integration. Simply supported beam is easy. How about a cantilever beam? I'm so sorry I didn't bring my ruler. A cantilever beam that bends like that. At this point here, when x is 0, y is 0, but I can't say when x is L, y is 0 anymore, can I? So what is our second boundary condition? What do we know? I'll draw my shape up here. So what's the second boundary condition we know? What do we know about the slope at a fixed support? It's 0. So our boundary conditions for a cantilever will be different. At x is 0, y is 0. At x is 0, dy dx is 0. So you would, of course, substitute into your slope equation to solve for your first one, and you would then substitute into your deflection equation to solve for your second. There is a third boundary condition for symmetrical systems, and you can use it if you wish to. For a symmetrically loaded beam, you know in the middle of the beam the deflection is maximum, so your slope is 0. So an alternative third boundary condition just for symmetrical beams with symmetrical loadings is the slope is 0 in the middle. Okay, so let us solve for our constants of integration. Here is our equation. When x is 0, y is 0. We substitute all the values in, we get C2 is 0. Is C2 always 0? Generally speaking, for a simply supported beam, it is. If you forget about it and don't write it down on your exam, okay, you will lose marks. So you need to come up with your constant and then you need to explain what boundary condition you're using and state it's 0. So for our second boundary condition, things are a little bit more complicated. It is non-zero. So in this case here, because we're dealing with general dimensions, L, you would stick the value of L in and solve for C1, and this is the wonderful equation you get. So what we have here is the general expression for the deflection of a simply supported beam carrying a uniformly distributed load as a function of the distance along the beam. So this expression now is valid for any beam of any length, with any value of load on. If I want to know what the deflection is a quarter of the way along, I would substitute in here L on 4. Yeah? So at any dimension of x. Hard? No. Now, fair enough, we have a general expression, but what we usually want to know is maximum stress, maximum deflection. So the maximum deflection in a beam occurs where the beam slope is 0. If you have a symmetrical system, where is the deflection maximum here? In the middle. So you could just substitute in a value of L on 2 here and calculate what the maximum deflection is. However, when you have a case where your loading or your structure is not symmetrical, you don't know where that maximum is, but you know at that point the slope is 0. Those equations? Yeah. Yeah, that's one exam question. Yeah. And we vary it. We make it different loads. We make it a cantilever. We make it a, yeah. I'll do an exam paper question once I get through this. Most definitely. Otherwise, why would I be boring you with it? So, in our example, we're just going to, in our example, we know the maximum deflection occurs in the middle, but let's check this. Let's substitute into our slope equation. So here's my slope equation. If I actually just say, let's check it at 0.4L, and I work out the slope, I get a value in terms of W and L on EI. If I, however, move along the beam and increase my value of X here, you can see my value is getting smaller, and it then goes from negative to positive. So that's telling me I know I've gone past my maximum point. So in finding maximums, if it's an easy equation, you can solve it mathematically. If it's got a cubic in it, you can solve by trial and error. In the exam, you won't be getting a cubic, okay? But you would be getting one that you could solve mathematically very easily, okay? So in this case here, if you did substitute in half the beam length, you would get a deflection of, you would get a slope of 0 to indicate that's where your maximum is. And for a simply supported beam with a uniformly distributed load, there's the value of your maximum deflection. Okay, it's 5WL to the 4th on 384 EI. Any honest, good structural engineer would be able to ramble that off. Any older one anyway, like me. Now, that was easy. That was a continuous load. How about when we have a discontinuous load? Remember, generally speaking, one equation is not enough for a discontinuous load, which is why I introduced you to singularity functions. So, in this case here, without singularity functions, we would require 2 equations for the moment, one before, one after, and you would have 2 equations to integrate. And it would be very painful. Hence why we have introduced singularity functions to you, because you can then work on integrating that one equation. So, and if you had a case where you had numerous point loads, you would then have to come up with lots of expressions, general expressions for your moment, within certain limits. So things could get very, very complicated. So we use singularity functions. So once again, just a reminder, what were these singularity functions? We put pointy brackets around whatever our x minus a term was, and whenever the term in the bracket was negative, we set it to 0. Whenever the term in the bracket is positive, we just treat it like a normal bracket. Now we're integrating singularity brackets. It's very important that you don't expand your brackets. So when you go through this integration process, you integrate it as you would a bracketed term. So there's the integration of x minus a. Now the other thing to note is, and we will come across brackets to the power of 0, and you all know any number to the power of 0 is equal to, okay? How come you all know that but you don't know where the centroid of a triangle is? Okay, it is. It's equal to 1. You stick any number in your calculator, it's always equal to 1. However, in this instance, you have to enforce the singularity rule first. Whenever that number in the bracket is negative, that term disappears. So in this instance, it's either going to be 0 or 1. If you follow those rules, this will be a breeze. So just follow the rules. Okay, so we're now going to look at the point load case. Just a single point load in the middle of the beam. Do we need a break yet? No, yes? Yeah, okay, I'll give you a 4-minute break. Come and ask questions if you have any.
It's always going to be x minus a, and a is always going to be the distance between your left and the point.
I'm about to do that, yeah. So you measured distances from the card. So therefore, with this point load here, when I measure moments here, it will be p times this distance.
So
this total distance is x, that's L8.2, so this distance will be x minus I.
So a is the distance between p and between the load and the card.
No, a is this distance in here. So I'm about to go over this, yeah? Can you see that? So I'm asking you, what is this? The moment is p times that distance. What is that distance? If I know that's x, and I know that's L8.2, what distance is x minus I?
The textbook we've got, is there anything in there on singularity functions, do you know?
On deflections, but I don't think there's singularity functions, but they would use normal brackets. So you can just
do you know any way that would help learn about singularity functions?
There are enough examples now I'm doing. This is the problem with the practice class, and there are solutions for them. There are singularity functions.
Yeah, so something that could do it like, singularity functions 101 kind of like step it
There's
through.
nothing else to it. That's why if you look in the book, they do deflection without singularity functions, which is the same way. They integrate a bracket. So no, I don't, because it's not hard. You won't need to go to a textbook, seriously.
No, it's still a bit confusing.
Yeah, but I just introduced it 1 minute ago. Yeah? It's not
but
hard.
it's been covered before.
Very briefly.
And
I didn't expect people to understand when I covered it before because there was no use of effectively. Because, once I showed you how to use the bracket, who cares about that? But now you have to know how to do it. So I'm going to do enough examples for you to become it. It's seriously not hard. If you are having problems, come, okay?
This is 0 if this is less than 0.
If it's ever negative?
If it's negative.
If it's negative, that bracket disappears.
Then how would you power 0 to 0?
Well, 0 to 0 is still 1. I should put if it's less than or equal to, so there should be an equal to there. You're saying if that's ever 0?
Yeah, so if this term is negative, then this becomes
So it
0.
should be less than or equal to, yeah.
Yeah, so this becomes 0.
Yeah.
But 0 to power 0 is bigger than 1.
Singularity rule says if it's less than or equal to, make it 0. So enforce the singularity rule first. Yes. Yeah? Yeah, singularity gets priority over.
Yeah, she can.
As soon as that term is negative or 0.
Bullshit.
Yes.
You came with me?
I can show you the physical management. Okay? Yes.
I have a question about a tutorial question. So,
It's all past now. Yeah.
I'll ask you later.
Yeah. Okay. Yeah.
Okay, it's 4 past. That was quick. How time flies. Okay. Singularity brackets are not hard. Seriously, I will give you enough examples. Okay. And I've just got my pen in a knot. Okay, so we are going to write one expression that's valid for the whole beam, and that will save us looking at a number of equations here. So let's go back. We cut the beam a distance x from the cut. In this case here we have a point load in the middle of the beam with a value of P down, so our two reactions are P on 2. So when I cut through my beam here, I cut as far right as possible and I draw my free body diagram that has all the known reactions, all the known loading and all the unknowns at the cut. So taking moments now here at the cut, you can see I'm cutting at a general distance x. The distance between the support and the load is L on 2, so this distance in here between the cut and the load is x minus L on 2, and that's where the singularity bracket comes in. So wherever you have an x minus something term, put it in pointy brackets. So we take moments here. We have our moment m, we have our point load P on 2 times the distance x. We have our second point load P, the actual acting load, times the distance x minus L on 2. And here is our expression for the moment. Now, can you see here, when x is less than L on 2, this term here would disappear. Can everyone see that? That's concentrating, that's listening. Yeah? What that means is, it means, I'll go back to this slide, it means I've cut it in here. See, when I cut it in there, my free body diagram is just px. Yeah? So I haven't actually, I've cut it before I've got to the point load. So that's why these singularity brackets are good, because they make terms disappear. And the reason these terms disappear is because you've cut the beam and you're considering a free body diagram where you haven't come across the load yet. So all it's doing is it's saying, we haven't come across this term yet, turn it off. We have come across it now, turn it back on. So it allows you to do that automatically. So it's a very, again, a very nice, mathematically speaking, way of doing things. So, as I said here, if you do cut before the point load, you get your expression just in terms of the reaction P. If you cut after the point load, not using singularity functions, just using normal brackets, you get this term here. Now, the term we got with our singularity bracket looked like so, which if I do substitute in when x is less than L on 2, this term here simplifies down to one term, which is the same as what we got. And if I substitute in whenever x is greater than L on 2, this singularity bracket, if I do expand it, simplifies down to this second expression. So it's just a very nice, easy way of coming up with an expression that has kinks in it. Okay? Okay, so moving on. There is the expression we got for our moment. So I've just pulled this equation out here now. Px on 2 minus p blah, blah, blah. There it is here. As well as equal in m, it's equal to ei, scribble that squared off, d2y dx squared. How do we get deflection? We integrate. We get slope first. Now remember, with these singularity brackets, you do not expand them. If you expand them, you lose the power to turn them off. So you can't expand them. So we integrate it as a whole. And I think once you've done this once or twice, you'll remember how to do that. You just square the whole bracketed term. Then we integrate it a second time. Before we integrate it a second time, this time we'll use that third possible boundary condition. So for this particular loading, our deflection is greatest in the middle, so we know our slope is 0 at the centre. So we're going to substitute into that equation and solve for C1. And we get a value for C1. Then we continue and integrate it a second time. And our second boundary condition we would use would be when x is 0, y is 0, and we substitute that in, and we get our second constant of integration equaling 0. And there now is the general expression for the deflection in a simply supported beam with a point load in the middle. Go home and wow everyone at home. Look at this. This is the equation for the deflection in a simply supported beam with a point load in the middle. They'll be going, wow, they're learning heaps at uni. Okay. To find the maximum deflection here, once again, because it is symmetrical, you would, wherever you want to know the deflection, you substitute in the value of x. In this case here, we want to know where it's maximum in the middle. If you substitute in L8.2, you get this expression here, a very nice, tidy, one-off expression. And you can find all of these values in the textbook, in any good textbook. Deflection equations. To save you sticking it in a computer package for the computer to work it out, it's a simple equation here. So you can see here, our deflection is a function of our load, which is obvious. It's a function of our span cubed. So can you see when our beam gets very long, because the deflection is a function of the span cubed, our deflection doesn't increase. If we go from a 1 metre beam to a 2 metre beam, our deflection doesn't double. It goes up by 1 to 2. It goes up 2 metres, 2 times 2 times 2, 8. Okay? It goes up 8-fold. So every time you increase the span, the deflection goes up significantly. And it is, of course, also a function of the inverse of the stiffness. The stiffer it is, the more it'll deflect. The less stiff it is, the less it will deflect. Okay, so here is a real-life case. We have a man on the bridge. He's standing in the middle. He weighs 100 kilo. We're ignoring the self-weight of the bridge. Shh. We know the Young's modulus of timber. We know the size of our plank. It's 200 by 40. And looking at it, our plank is sitting 200 wide, 40 deep. So when we have to calculate our moment of inertia here, we're talking about bending about the XX axis. So our I here would be 200 times 40 cubed on 12. Remembering that when we use our expression, BD cubed on 12, B is always parallel to the axis of bending. I know you weren't laughing at that because that wasn't funny, so you're talking. Shush. So we get our general expression for the deflection that we previously derived for point load. And very importantly, when you do this, once again, just be consistent with your units. I don't care what units you work in, as long as they are consistent. So I would suggest you work in kilonewtons and metres. You could also work in newtons and millimetres. It is up to you. Because we're going to work in kilonewtons and metres, we're going to change our load into kilonewtons, 1 kilonewton, and we'll keep our length as 4 metres. Our Young's modulus has been given to us in megapascals, so we need to convert it to kilopascals. When we work out a moment of inertia, because we're working in metres, you would say 0.2 times 0.04 to get the value in metres. And when we plug into our equation, we get our deflection, and it's 125 mil, 0.125 metres. Now, if you were then going on and doing a serviceability design here, you would then say, oh, sorry, it's a negative because it's downwards. You would then say, okay, our maximum deflection is 125 with the full live load. In this case here, let's take 0.7 of that, which is 87.5 millimetres. Our allowable deflection is span on 250 is 16 millimetres, so thus our bridge fails. But it's not a bridge, it's a plank of wood, so who cares how much it deflects. But if this was a proper bridge, you would put more than one man in the middle, okay? You would say you have got, 4 kPa, 5 kPa of load on that bridge, and you were designed for that. And that's basically the process you're going to go through. However, in your project, you don't know what your moment of inertia is. That is your unknown. Okay, moving on. Things progressively do get, mathematically speaking, a little bit harder and harder. So I've started off easy. Now we have to look at what happens if you have a discontinuous, uniformly distributed load. Can you just accept this and not question it, not go why, and not come up and say, is there an easier way of doing it? Okay? There are 2 ways of doing it. But what you need to do is, whenever you have a load, if I was coming up with an equation, I would cut this as far left as possible. Now, whenever you have that situation and your uniformly distributed load does not run into the cut, you need to continue it into the cut. Why? Why are we doing this? We are doing this so we can come up with one expression that's valid for the whole beam. Okay, that's why we're doing it. Otherwise, you would have to do it with two expressions. So, we run our load into the cut, and of course we can't go adding load, so we have to take away from below. So this load down here is an upwards load. So in effect, these two have the same loading on them. But in order to get the maths right, we just continue the loading to the cut and we take it away from below. And then we make a cut, a distance x, just as we did before. So if we look at our loading here, we have 20 newtons per metre over the centre 3 metres, so that's a point load of 60 newtons when we're looking at reactions. So our reaction is 30, so we're going to make our cut here. So when I make my cut here, this distance is x. Tell me, what is that distance equal to? X minus 3. I put it in pointy brackets. What is this third distance in here equal to? Yeah, x minus 6. So on this next page, you will see x, x minus 3, x minus 6 on here. And then you take moments at the cut. So, taking moments at the cut now, we have m. This first term relates to our point load reaction, force times distance, 30 times x. Then this second term relates to the loading on the top. So we have a total load now down here of not 20 times 3, 20 times 6. The total load down here is 20 times x minus 3. And where is it acting? It's acting in the middle of x minus 3. So it's acting at x minus 3 on 2. Concentrate, you'll get it right, yeah? So when we deal with our load down the bottom, our blue load now, what is the total load? Well, it's negative because it's a load up, was causing a moment clockwise. 20 times this distance here was x minus 6. Where is it acting? X minus 6 on 2. Now, I don't want you to get your knickers in a knot about where is it acting. Basically, once you get your load, 20 times x minus 3, is everyone happy they could get the load? All you need to do is square it and divide it by 2. Because the distance is always half of that bracketed term. Does that make sense? You've got to think about it, but it's as simple as that. Okay, here is our complicated expression. Things are getting more complicated, but mathematically all we do is we integrate it once to get the slope. Once again, we have a symmetrical system. So in the middle of the beam our slope is 0 and we solve for our first constant of integration. Then we integrate it a second time and the boundary condition of x is 0, y is 0 comes up with a second constant of integration equal to 0, and there is our general expression. So this is now the general expression for a 9 metre long beam with a uniformly distributed load of 20 newtons per metre in the centre third of the span. And that's the process you need to go to, and thank God computers are around, and generally speaking, computers do that for you. However, if your boss says, tell me very quickly, or you're in a meeting with architects and quantity surveyors and they say to you, roughly, how big do you think that beam has to be? You can't say, I'll get back to you in 20 minutes or 30 minutes and go to a computer. You've got to be able to whip up a quick equation and do a calculation quickly to give them an idea. So it's important you don't forget this. Okay. So maximum deflection is in the middle. As in our previous example, let's assume we have our timber plank just for our EI value. And this time round our deflection would be 81 mils, so it's still too high. Now, continuing on from example 3, here's another example. We have a discontinuous load, but it actually starts at the left-hand end. So, once again, we cut it as far right as possible, and we draw that free body diagram. So once again, you would have to add load on the top and take it away from below. There is an option, however, if your load does continue all the way in the other direction, and that would be to create a free body diagram cut in as far right as possible. And if you do that, in that case you don't have to add and take away. Either or is fine. What you have to be clear about here is with your boundary conditions. In this case here, this would be x is 0, and in this instance here, this end is x is 0. So you then have to be clear where you take x from. Okay. We have to put a moment on now. Do you want me to show you something more? Not yet. We'll do one more example, and then I'll tell you how important it is you know how to do deflections. Okay, we'll do this one, and then I'll show you something a bit more interesting. I have lots of problems to do. The only way to show you is through worked examples. I have a moment applied to my beam. What a bummer. When would that happen in reality? Not sure, but you have to know how to do it, okay, to pass this subject. Oh, no, you would get. There are situations, but they're not common, okay? We have a moment. Can you tell me what the reactions are there? You should be very quickly able to tell me what the reactions are. That, I've only got my pen, moment is causing my beam to spin like so. People in the back see it? So, at A, tell me, will the reaction be up or down? Down. Okay? And thus, for forces in the y direction, this reaction must be up, and those two reactions must be equal and opposite. What are they equal to? 12 divided by 8. Taking moments at A, it's a roller end support. All the moments at A equal 0. The moment is 12 kilonewton meters. It's going clockwise, so it's negative. Then I have By, I'll call it B, my reaction here. Force times distance times 8 meters. That's causing anti-clockwise rotation equals 0. And as you can see here, B is equal to 12 on 8, which is 1.5. How many of you knew that? Okay. If you had no idea, make sure that's clear to you, okay? That's something that you should be able to do. Okay. So, what do? We have to cut the beam as far right as possible and draw our free body diagram. Without that, you can't do anything else. That in itself will get you 1 mark on the exam. So if you go, I don't know how to do deflections, okay, Lizzie said if I draw a free body diagram, I'll get a mark. At least get that far. But hopefully once you get your free body diagram, then you're going to calm down and go, oh, all I have to do is take moments. So not every week, but in the very beginning, I think I said to you, I'm not actually teaching you much new. In doing this method, we're using free body diagrams and equilibrium again. We use free body diagrams and equilibrium to calculate reactions. We use free body diagrams and equilibrium to calculate truss forces. We use free body diagrams and equilibrium for method of joints and method of sections. We use it again to calculate internal moments, and we're using it again to come up with our deflection equation. 80% of this course is understanding free body diagrams and equilibrium. If you understand it, your life will be easy in this subject and in next year's subjects. Okay, I've rambled enough and I've preached enough, and stop it, Lizzie. Let's get back down to what we have to know. Let's take moments at the cut. So here is my free body diagram. I have my distance x in here. That's 4. This distance here is x minus 4. Now here is the next thing. Normally a moment, if I was saying moments here, I would say I have m and then I have minus 12. We now, if your moment is not at the very end, you can't just call it 12 anymore. You have to multiply it by distance to the power of 0. Why am I multiplying it by distance to the power of 0? That's because I want the ability to turn it on or off. Remember, distance to the power of 0 is either 1 or 0. It's not a distance, it's either a 1 or a 0. It's an on-off switch. If I actually cut my beam in here, have I come across the 12 yet? No, it would be switched off. It would disappear. So we multiply it by distance to the power of 0. Here is our moment equation here. We have m, we have our force, 1.5 times distance x. We have our moment times x minus 4 to the power of 0. So this third term here is either minus 12 or 0. It becomes 0. When does it equal 0? When x is less than 4. When I cut the beam in here. No. What did I do? You need to... Okay, have a break. Good point. Have a break. Don't come and ask me any questions. I think my battery ran out. No, I'm not going to panic. Ooh, no, I don't want that one. Okay. Okay. That's not good, but we have the document camp. Whoa! Oh, I know. Sorry, I think I didn't look at the charge on my on my computer. Or my battery's dying. Okay, we will continue and do it less high tech, but we need to do some more problems. I can't show you that really interesting thing. I'll have to show you next week. Oh, you didn't really care anyway. Yes, you did. No, I know you did. I'm sorry. I'll show you two. No, next week's our bridge testing. I'll show you on Monday in the 1 hour lecture. I'll break up the 1 hour lecture. Okay. Oh, I've got to use the right mouse though. Okay. We'll survive. I just can't write on this. Okay, so we have our expression for our moment here. Now, before we do start integrating this actually is the expression for our bending moment. And be aware of that. So if I actually had asked you to draw this bending moment diagram here, and you actually found it a little bit difficult, if you went, I have absolutely no idea what that bending moment was, you could actually come up with your mathematical expression. And you can see here you substitute values in. When x is 0, m would be equal to 0. When x is 1, m would be equal to 1.5 times 1, and you would get that value in there. And substituting in, you would get this shape here. So isn't it amazing that that expression is the expression for this wonderful shape here? Yeah. Okay, so there's your bending moment diagram. Remember, when you have a moment applied to the beam, that's when you get a step in your bending moment diagram. And this expression would bear that out. Okay, so we get our expression for our moment. We integrate once. We integrate a second time. As I said, I know you can all integrate. We apply our boundary conditions. Once again, our boundary conditions are that the deflection at the two supports is 0. So when x is 0, y is 0, and when x is 4 metres, that should actually say 8 metres, y is 0. And substituting in, we get our two boundary conditions. So what would the deflected shape look like here? It's shown here in that red dashed line. And you could calculate all those values. So if you would put in when x is 4 metres at the centre of the beam, you would find that the deflection is 0. You've only got a moment applied. That moment isn't causing a downwards load or an upwards load. So you end up getting a positive value here at 2 metres of 6 and a negative value here at 6 metres equal to minus 6. These values, it's just that they've been left in terms of EI. Okay? So, singularity functions, when you have a moment, the moment is multiplied by distance to the power of 0. Whenever you have a single point load, you multiply it by distance to the power of 1, force times distance. When you have a uniformly distributed load, you will find that you always have a parabola, an x minus something squared term next to it. Now these, I said, are general formulas that you will find in any structural textbook. These are standard formulas that in my day you would have memorised. You wouldn't bother to look them up. You would know what they are. And these are deflections for the maximum. Sorry, these are maximum deflections for various beam types. Okay, let's do a real high-rise example. You're in a meeting and you're being asked roughly how much will this structure deflect horizontally under wind load. And you're sitting there going, crapping your pants going, I have absolutely no idea. Then you go, no, remain calm here. I'm going to go back to my basic understanding of equilibrium and deflections, and I'm going to work it out. So how far will the building sway? Now in saying that, we're going to come up with an answer in 5 minutes. In the terms of the design of this structure, it will be a huge analysis. okay, with huge numbers in, running. It would take ages to build the model. They would do it, and they're going to get a deflection, and you're going to probably be within 80% of that value, 80, 90%, okay? I could be making this up, but it sounds good, doesn't it? Okay, how far will the building sway in a wind gust if the wind pressure is 0.7 kPa? So let's work through this. 0.7 kPa, 70 kilograms per metre squared. So it's a big wind load on the side of this building. So this structure, being designed by a wonderful engineer, they know let's taper in the size of the building because we have less area carrying that load. Now this structure here is, of course, it's a cantilever. There's the wind load acting on it. So of course we don't want to have a lot of load here because we know from our bending moment diagram. Does this get recorded? No, I don't think. Actually, I'm not sure. Yeah, I think this side gets recorded. Not 100% sure. That side? Oh, okay. Okay, I think I need to swap them then. Right. And if I go back to laptop and go left, no, lectern, hang on. But you know what's going to happen? You're going to watch this online, and we would be recording this side, and now we're not. So it was probably right in the first place. I'm not sure. For those people that aren't here, sorry. Okay? They're laughing at a joke, everyone that's not here. Don't worry about it. Okay, here's our building here. Here's our cantilever. Let's work out the wind pressure. So our building reduces in its width. So when we work out the actual wind load in terms of kilonewton per metre, we multiply by the width of the building. So at the top it's 20 metres wide, then it becomes 40 metres wide, then it becomes 120 metres wide. So therefore you can see our uniformly distributed load here tapers in, it steps in. And here's our building deforming. Now what actually stops the building? Where's the stiffness in the building coming from? That, of course, is a function of how tall the building is. In a low-rise building, the frame itself would provide the lateral stability. In a mid-range high building, the concrete core is what you rely on it for bending stiffness. So you have all the floors and the columns in there, but you don't rely on them for your lateral sway stiffness. As the building gets higher, you have to rely on more stiffness in your building. You'll then have cross bracing sometimes on the outside face of the buildings that looks like an architectural feature, but it's also there to ensure that your building is actually acting as a truss as well. So in this instance here, it's our concrete core that we're going to assume is actually providing the strength to our building. So our core is, and that concrete core I'm talking about is the escalator shaft and the stair shaft, the stairwell. Yeah? So those walls are usually very thick. Here we're saying that concrete core where the escalators and the stairwells are, it's roughly a square shape of 6 by 10 metres. And the concrete walls are 400 mil thick. So we know Young's modulus of concrete, and now you can just work out what your moment of inertia I is. Isn't this cool how we can simplify all this down? That's a $1 billion structure. And we can do a quick calculation. Okay, moment of inertia here is your BD cubed on 12. I'm dealing in metres here, so my final answer is in metres. So it's the outside rectangle, take away the inside rectangle. Now, of course, if I'm bending about the YY or the XX, I'm going to get different moments of inertias. So conservatively, we're going to assume we have bending about the YY axis because that gives us our smaller moment of inertia. Does that make sense? Because it's B d cubed on 12. So we are d cubing the 6 metres, not the 10 metres. Okay, so here is my loading. Remember I cut the beam, we calculate our reactions based on that loading. And remember our uniformly distributed load has to be continuous. But we've got it stepping here. So what we're going to do is we're going to assume our loading occurs in 3 parts. We first say we have a uniform load of 84 kilonewtons per metre. Then we're going to take away this 64. Because when you take 56 away from 64, what do you get? 28. Yeah? Then it drops another second amount, so then we take away a 4, the 13. Because 64, take away 56, take away 14, gives you 14. So our loading now is made up of 3 components. So, believe me, this is the equation. Okay, let's run through it here. So this is the equation. I'm going to turn my structure around here. And I have a load of 84 kilonewtons per metre, and then I have a load here of 56 kilonewtons per metre, and then I have a further load here underneath of 14 kilonewtons per metre. So when I draw my free body diagram, I have my reaction term here, which we said was 7840. We have our moment. We have this load here of 84. There's my cut. I have this load here of 56, and that's acting over a distance of x minus what? How tall was my building? So we're having that act over x minus 80 metres. Yeah? And then I have my third load in here, and that is acting over x minus 200 metres. Apologies for this. So if we do take moments at our cut here, you can see this first term here. That's my reaction. The units have been changed, but there's my 7.8 times x, force times distance. This 627 is my moment. Can you see we've multiplied it by distance to the power of 0? There is no need to multiply our moment by distance to the power of 0 if the moment is at the very end. Because is that term in there ever negative? No? So it stays on. So it's only when your moment is applied within the beam that it's essential you multiply it by distance to the power of 0. Then we have our third term, and that is this 84 kilonewton, total load 84 times x, acting in the middle of x. So there is your 84x squared term. Then we have our 56 term and our other term. So we integrate it twice. What are our boundary conditions? Our boundary conditions are when x is 0, y is 0. This, of course, is the top of my tower. So the second boundary condition would relate to the slope here. So here are my 2 boundary conditions, when x is 0, y is 0. So not going to do all that maths from you, but basically there is our equation. And our building that's 240 metres tall deflects 3.63 metres. I think that's a bit much. Okay? But there's a quick calculation. So you would go, okay, we either require the concrete core to be bigger, or we have to look at integrating something else to stiffen up our structure. By looking at cross-bracing, by making our framework also contribute to the stiffness. And that's the sort of calculations you would go through. Okay, I'm now going to look at a past exam paper. I'll give you a break. And while I'm giving you a break, I need someone to give me a piece of paper to write on. Don't say no one has a piece of paper, okay? Don't need anything. Thank you very much. Actually, I'll be slack here. Okay, here's an exam question. Have a read of it. So this is a typical exam question. We have a beam, simply supported beam, and the point load is not in the middle of the beam. It's off centre, so thus we don't know exactly where the maximum deflection occurs. And the question is to derive the equation for the deflection of the beam, the general equation, and then locate and determine the maximum deflection in the beam. And it tells you, because they were nice that year, that the maximum deflection occurs within BC. So the maximum deflection occurs somewhere there. So basically, if I was drawing the deflected shape here, the maximum deflection occurs here. And at this point, hopefully, that's made clear to you. People automatically say, oh, the maximum deflection occurs under the point load. Not true. Only if it's symmetrical. How can the maximum deflection occur where the moment's maximum? They think it occurs where the moment's maximum when those two variables are two integrations apart. To get from moment to deflection, we integrate twice. Okay, so you calculate your reactions first, and then you draw a free body diagram. Need to see this free body diagram. You need to draw that. You also need to get your reactions correct. Very important you get your reactions correct. The other thing to note now is, before you go any further, you go, what units will we work in? Now, I personally, when I get here, even though I always go newtons and millimetres, megapascals, newtons, metres, mega and pascals, when it comes to deflection, I like to stay working in kilonewtons and metres. Because if you start changing your length from metres into millimetres, you have heaps of zeros in there. So I stay in newtons and metres, and it very simply, you just need to convert your EI value here, which is in newton millimetres squared, to kilonewton metres squared. And that is a simple conversion where you have a factor of 10 to the 9 difference. So 1 newton is a thousandth of a kilonewton, 1 millimetre is a thousandth of a metre, and that's squared. So you just have to remember this 10 to the minus 9 factor. Okay, we draw our free body diagram and we take moments at the cut. So in this case here we have our x. What's not on this diagram is this distance in here, which is your x minus 4, and you know you have to put that in singularity brackets. So taking moments at the cut, you have your reaction 30 times your distance x and your action of 50 times the distance. And then you just start integrating. Integrate once, integrate a second time. You have your two constants of integration. Boundary conditions, very simply, when x is 0, y is 0. When x is 10, y is 0. So that first part of the question I think was maybe worth 6 or 7 marks. And then you end up with your general expression. So we want to see an expression that looks like what? So here is the part A done. Come up with a general expression for your deflection in the beam. Okay, now the next bit. When you find in the exam or whatever, there's a part A and a part B. Usually the part A is an easier thing that we expect everyone to be able to do, and part B is slightly more challenging. So in this part B it says, where is the deflection maximum? How do you work out where the deflection is maximum? Deflection is maximum where your slope dy dx is equal to 0. So that means we go back into our slope equation. So we come back into our slope equation, and we set it to 0. So we set that term in here. Where am I? And we have a value for C1, so we put that value in there to 0. Now, we then have to set this term to 0, and we've got lots of quadratics in there. Now, it's been hinted, we've been given this wonderful hint that says the maximum deflection occurs within BC. Now, BC, let's come back down here. Oh, where are we? You can see BC is in the second part of this beam, where x is greater than 4. So thus, is this term ever negative? Now it's not negative. We can then just treat it like a normal bracket and expand it. So in doing that, let's see where I'm at. Oh, maximum deflection. We get that expression for our slope up here. We set it to 0. We get a quadratic expression. And you're all expected to know that x squared plus, ax squared plus bx plus c, how to solve that. Minus b plus or minus the square root. You all know what I'm talking about, of b squared minus 4ac on 2a. You all know what I'm talking about? Yeah? Yep. So you solve your expression and you get a distance. Now what I want to point out to you is sometimes we are not kind to you and we don't tell you where the maximum deflection occurs. So over here in green, say we didn't know where the maximum deflection occurs. The easy thing would be to assume it occurred in this region here, where x is less than 4. So if we assume it occurs in the region, I want to get that all up there, where x is less than 4, if you look at your slope equation, that second term cancels out. So your slope equation here simplifies down dramatically. And you can solve for x straight away. It's just the square root of 320 on 15. Now, if you do that, if you would have gone down that path, you would have got a value of 4.61, which is greater than 4. So it's outside the limits. So therefore your maximum deflection doesn't occur. So that's the numbers telling you your maximum deflection doesn't occur within that range. It occurs outside that range. So you're in the wrong region. You have to then go look at the region between B and C. Make sense? Okay. So finally in this question, it asks you to calculate the maximum deflection. So you would substitute your values in and end up with getting a deflection. And that question is done. Yeah? Okay, let me see what else I've got and how hard this is going to be for me to do it this way. I'll give you another 2-minute break and I'll sort myself out. We need, because of time constraints, to continue a little bit more. Further. Okay. I don't like to ever be accused. Sometimes on feedback it says they always did the really simple equations in the lecture and then never did any hard ones. I like to do the hard ones in the lecture. So we have a beam here with an internal pin again, my favourite. With pin support, roller support, pin support. Don't yawn. Or yawn quietly, that's rude. I'm starting to think you're bored. That wouldn't be the case. Okay, we have an internal pin. Before we can do anything, we need to calculate all our reactions. We'll probably just draw the bending moment and shear force for this, and then we might call it quits. Okay, in this system here, in order to calculate reactions, which side are you going to start off looking at? The right? Okay, can you see that's pretty symmetrical? So tell me what this support reaction is there. Ah. Yeah, I expect you to be able to memorise that and see that. Okay, did you see the beam anyway? Yeah, you could see that. Okay, so A, B, C, and I call the internal pin D. We know we're going to look at the right-hand side first. What is the reaction C equal to? 10. Everyone happy with that? Simply supported beam, load in the middle. That reaction here is 10 kilonewtons. Once you have that reaction, you can either move to the left-hand side or look at it as a whole. I am just going to give you the values now. If you are still having problems with this, make sure you can get these values when you look at this at home. Here are the reactions. I'm aware you all haven't done your practice class this week, which is going over, finishing up your shear force and bending moment diagrams. So for some of you, you'll go easy peasy. We did that this week. Others you'll go, core, I don't know what she's talking about. And when you do your problems, your practice class tomorrow or Friday, you will. Draw the shear force diagram for me. Start at the left-hand end, follow the loads. Tell me what to do. Up, I hear an up. Good. Tell me what to do. Diagonally down. Excellent. And you all know this value here is 60 minus 28. And we're going to step up how much here? Good. To 10. And what are we going to do now? Continue. And you're going to tell me to stop. Go down, 10, across, up. Okay, corresponding bending moment diagram. B is equal to dm dx. A positive shear force is an upwards or a downward slope. Okay, so I go down, up, down, down, up. Now, where is my bending moment 0? A? Where else? C and D. It's an internal pin. Good. This is like a join the dots, but more fun. When my shear force is linear, what's my bending moment? Okay, and when my shear force is constant, what's my bending moment? Okay, close your eyes if you haven't got paper in front of you and sketch that shape. Well, you don't have to close your eyes. I'm 0 here and I know it slopes down and I know it's linear. So what's it look like? That. What's this value here equal to? 30. Because I'm coming from the left-hand side, it's the minus of the area. So that's 30. I know it has to start sloping up. You know it has to end up at 0 here. So I know that's just going to come up. And it's going to continue up. Continue up with the same slope. Why is it continuing up with the same slope? According to my shear force diagram, the value throughout here is 10. This value of 10 is telling me the slope, the gradient of this line is 10. So it continues up with the same slope. And then what am I doing? Big Dipper. Except that's meant to line up with that. Hey, I'm under pressure here. I forgot to charge my battery. No, I did. Must be sick. Okay, so this area in here, I'll call that area 1. I'll leave you to work. Oh, no, I won't leave you to work it out. That value there is 40.129. To calculate that area, I need that distance. How do I calculate that distance? Rise on run, the slope of this line, the gradient of the shear force, is equal to our load, 10 kilonewton per metre. So therefore that line in there is 2.833, and there's my bending moment shear force diagram. Okay, I am going to just do another 5 minutes and then set you as homework. Homework, working at home, learning at home. What do we call it? Learning at home. And I want you all to do it because we're a bit short on time because of the bridge testing next Wednesday. So this is the serious phase. I really want you all to do it, okay? Because I haven't got time to cover it properly. Okay, deflected shape. How the hell do we do this? We have an internal pin in here. What do we do? What we're going to do is we are going to look at it, you are going to look at it in 2 parts. Okay, that's the internal pin. That's the load on here, 20. So you need to look at this in 2 parts. Now we said that reaction here was 10, so we know the shear in the pin here is 10. And if we go up on one side, it's down on the other side. So if you imagine this side now, we have a load pushing it down, and then this shear 10 is like a load, it's also pushing it down. So could you see that deflected shape? Yeah? Now, I'm not sure if that load is big enough to push it down below or if it remains above. But from my bending moment diagram, what I do know, because my moment is tension on the bottom, I know I have tension on the bottom there, and then I have tension on the top. How do I know that? Remember, where the moment is 0, that's where I have my point of inflection. And next week what we will do is we'll calculate how to calculate where that point of inflection is. Okay, so what you are going to do is you are going to come up with the mathematical expression of the left-hand side. What are your boundary conditions? When x is 0, y is 0, that's 6 metres. When x is 0, 6, y is 0. And from that, you're going to try and calculate for me the maximum deflection under the uniformly distributed load. Now, all those people not sitting there writing this down, come on, you're doing this as learning at home. Write the question down, okay? And you're also going to tell me what the deflection at the tip is. Now, why do I need to know what the deflection at the tip is? Let's temporarily move across to the right-hand side. I'm now looking at this side. What are my boundary conditions over on this side? Now I'm going to take x from here again. I'm treating it as a standalone. But can I say on this side when x is 0, y is 0? No, because that's not a support there. That's the point that moves up and down. So when x is 0 here, y is equal to the deflection at the tip. Can you see that? And then here you would say when x is, that's 3 metres and that's 3 metres. When x is 6 metres, y is equal to 0. So you might have said to me, oh, this left-hand side is really hard. I'm going to start on the right-hand side. You can't, because you haven't got 2 boundary conditions, you know. You can't say this is symmetrical loading, the slope is 0 in the middle, because this point here, the internal pin, is not a fixed point. Okay? So I want you to get as far as finish this right-hand side, calculate the maximum deflection under the UDL load. To do that, you're going to have to set the slope dy dx equal to 0 and solve for x. Okay? Do your homework. And please do it because I don't have time to do all of this in the lecture. Okay? Apologies for the slight technical problem. I think we'll finish there. If anyone has any questions, come and see me.